So let's consider another issue. Early on, we were worried about whether we should deprotonate this carbon or this carbon. Well, suppose we had deprotonated this carbon, then it would have attacked the number 2. So let's use the finger method to count how many atoms would have been in that ring. If the number 8 had attacked the number 2, how many atoms would be in that ring? We won't actually draw the full ring, we just want to count how many atoms would be in the ring if the number 8 attacked the number 2.
Seven.
Let's see if I can confirm that. So I'll start by counting the number 8. That would be forming a bond to the number 2. So that's 2 atoms, 3, 4, 5, 6, 7. And then we're back to where we started. So you're right, a 7-membered ring.
All right.
So who is it better to deprotonate, the number 6 or the number 8?
The number 6.
Because that will form the 5-membered ring. So that answers the question and the concern that you had at the beginning. You weren't sure which alpha carbon to deprotonate. Well, now we know why we deprotonated this one and not this one. When we deprotonate this alpha carbon, it can form a happy ring. If we deprotonate this alpha carbon, there's nothing good for it to do because it can only form a less happy 7-membered ring. So this is something to watch out for. If you have more than one alpha carbon you can deprotonate for an intramolecular condensation, you want to deprotonate the one that would allow you to form the 5 or 6-membered ring. One thing that seems to be obvious to you is obviously this alpha carbon isn't going to attack its own carbonyl. It's going to attack this other carbonyl over here. It wouldn't make any sense to try to attack here. Now, of course, it doesn't really matter whether we deprotonate this carbon or this one, because they're equivalent to each other. The important thing, though, is we saw we want to deprotonate one of the internal alpha carbons, not the external ones, because in this case, they form a better ring. Does that make sense?
Yes.
Well, we've still only done the very first step of our aldol condensation, so let's continue what would be a reasonable next step. Let's try to draw the mechanism for the next step.
And a deprotonation of the alpha carbon at number 6, or the alpha hydrogen.
Let's see, which picture are you looking at? This one. Now, who's the reactive atom in the picture that you're looking at?
The number 7.
Now, the reactive atom here is the one with the charge. It's always really
Oh,
important
sorry.
to focus on the atom with the charge.
Yeah.
This is what we have to deal with right now. We have to deal with this charge. Somehow this oxygen would like to get rid of this charge over here. Let's also take a look at the handout for when we get stuck in the steps. So let's take a look at the aldol condensation page of the handout. Okay, so we're on page 3, and I guess we're doing the middle because, well, no, I guess we can still be up here so far. So what have we done so far? We had the nucleophilic alpha carbon loses a proton. The nucleophile attacks the carbonyl carbon, breaking the pi bond. So what's the next step? Do you see how this is what we've done so far?
Okay, I'm not sure where the chart goes after here. It looks like this ends. It goes over here.
No, so we started with the nucleophile losing the proton. That was when the alpha carbon here lost the proton.
Mm-hmm.
I put that in parentheses just because I like to put protonations and deprotonations in parentheses, but that doesn't mean they're not important. I just like to put the protonations and deprotonations in parentheses. Then out of
so the
parentheses,
carbonyl it's gonna gain a proton.
yeah, who's going to gain the proton?
The oxygen.
The carbonyl oxygen. We were just talking about how this is the reactive atom and has to get rid of its negative charge some way. But the handout tells us that it can get rid of that charge by gaining a proton.
Okay.
Okay. And who can it take the proton from? Well, it can take it from the water that we generated in this step. This is a complicated mechanism, so anytime you get a little bit stuck, it's good to try to use the handout to see where the next step is. to keep putting in my labels so I can see what happened here. I can still see that the alpha carbon attacked this former carbonyl. And now we regenerated our base catalyst. So we saw how we can use the handout when we get stuck, or you could just use your general model here. Remember that in our general model, first the nucleophile attacks, and then the oxygen has to pick up a proton to finish at category 1. So this would be the category 1 aldol condensation. So if we were under cold conditions, this would be our final product. Remember that last time we also saw that there were names for the products from aldol reactions and condensations. Do you remember what do we call this type of collection of functional groups here?
It's going to be a beta hydroxy ketone.
Yeah, that's very logical. The hydroxy is on the beta carbon, so it's a beta hydroxy ketone. That's right. Under cold conditions, this would be our final product. You can see the top half of page 3 here. It just tells you what to do under cold conditions. So under cold conditions would be done, and we'd get a beta hydroxyaldehyde ketone. So the step that gave you trouble here was the step in parentheses, when the carbonyl oxygen gains the proton. Now let's go on and imagine that in fact this was under hot conditions. If this was under hot conditions, what would happen next?
Is that on here? I don't actually see it on the chart.
So let's see, the top half of page 3 is cold conditions,
Okay, good.
and then this, now we're in the hot conditions.
Okay.
So what have we done so far? Well, under hot conditions, we would still have started with the same 3 steps as before.
Mhm.
So these 3 steps here are the same as these 3 steps over here, and now we have our intermediate, the beta hydroxyaldehyde or ketone. So what's the next step now that we're under the hot conditions?
Well, it says the nucleophile loses a hydrogen.
That's right. And who is the nucleophilic atom in this reaction?
The alpha carbon.
That's right. That's why we keep labeling the alpha carbon, or at least I put that in quotation marks because it's going to become the nucleophilic atom
Okay.
anyway. Okay. So that's the step we have to show. We have to show some mechanism by which the alpha carbon can lose a proton. That's right. We can draw an intermediate from that step. Good. And we have to figure out what happens next. Now we have to decide what would happen next with this intermediate.
The hydroxy is going to leave.
So let's show the mechanism for that.
No, that's not right.
We can consult the handout. Or what was the step that we just did in the handout?
We deprotonated the alpha carbon.
That's right. So point to where we are in the handout now. Okay? So let's see if that helps us to see what to do.
It says it leaves as a hydroxide.
Good. What else does it say?
And then nucleophilic attack of carbonyl C at a second time forming.
Right. And notice the word while here and the dots, which is intended to indicate that these are happening at the same time.
Okay.
This happens while this is happening down here.
Okay.
So how can we put in some arrows for the nucleophile attacking the carbonyl carbon the second time?
Yeah, I'm gonna have
Okay.
a lot of blank for somebody.
Okay, well, let's see if the handout can help us. It says the carbonyl oxygen leaves as hydroxide. So can you show an arrow for that? What would the arrow look like? That's right.
Ah. There we go.
Right. While
the nucleophile attacks the carbonyl carbon a second time, forming a pi bond. Who do I mean by the nucleophile? Who is the nucleophilic atom in an aldol condensation?
The alpha carbon.
That's right. That's why we keep labeling this alpha here, so we don't lose track of it. Oh, I put the arrow in the wrong place on the board. Okay, so yeah, things, the handout lays out step by step what the mechanism is, but it can be a little cryptic until you've seen a few examples. So what it says is that the carbonyl oxygen leaves as hydroxide, while at the same time the alpha carbon attacks the carbonyl carbon a second time. Well, this is how it does that attack, by donating the electrons here.